I want you to put yourself in the shoes of, like, a deep space mission director, just for a minute.
Okay, high-stress job.
Oh,
Yeah.
incredibly high stress.
Yeah.
You're sitting there in mission control, looking up at the telemetry data for this autonomous probe you just launched.
Right.
And it is, without a doubt, the most sophisticated piece of artificial intelligence ever built. And it's heading out toward the edge of our solar system. And eventually it's going beyond it.
Which is a massive investment.
Exactly, a multi-billion-dollar asset. So as the person responsible for it, your mind naturally goes to, well, the obvious physical threats.
Yeah, you're constantly worrying about, is a micrometeoroid going to hit it?
Yes. Or
Yeah.
like degradation in the primary thrusters, or maybe some severe radiation from a solar flare just frying the circuitry.
Right, because those are sort of the standard engineering hurdles of spaceflight. The physical environment out there is just inherently hostile to delicate machinery.
Right.
Which is, why we build all those redundancies into the hardware.
But there's a completely different kind of threat that we are going to explore in today's deep dive.
Mm-hmm.
And it's not a physical object colliding with the probe.
No, it's not.
And it isn't even like a traditional software bug written by some tired programmer at 3 a.m.
Right.
We are looking at a scenario where the biggest threat to your mission is the fact that time itself, like the actual physical flow of seconds and minutes, is moving at a completely different rate for your spacecraft than it is for you sitting in mission control.
And that just feels so counterintuitive, right? Because down here on Earth, we basically treat time as an absolute constant. A second is a second.
Yeah, always.
But as we push our autonomous systems further out and, into much more extreme environments, the theoretical physics of the early 20th century, specifically Einstein's theories of relativity.
Right, heavy stuff.
Yeah, the really heavy stuff. It's suddenly becoming this urgent, very practical engineering problem for the 21st century.
And to understand why this is happening and why you should care about it, we're diving into this fascinating research proposal. It was published in April 2026 by Louis Bonaldi.
Titled Temporal Frame Divergence in Autonomous Deep Space Systems.
Catchy title, I know. But the goal of this deep dive is to understand how we are being forced to completely rethink the fundamental architecture of artificial intelligence for deep space exploration.
We basically have to figure out how to program a machine to operate when its very experience of reality is warping.
Mind-bending.
It really is. And Bonaldi's work, it's essentially a massive wake-up call for the aerospace community.
Because we've been ignoring it.
Yeah, for decades, actually. We've been building these autonomous frameworks with this massive, completely unacknowledged blind spot.
Wow.
If we expect machines to operate independently in deep space, making split-second decisions without human intervention, we have to address this. Or we risk these catastrophic mission failures that, honestly, our current diagnostics wouldn't even be able to detect.
Okay, so let's start by clearing up a misconception. Because I think, traditionally, engineers treat deep space communication as just a latency issue, right?
Yes, just the delay.
Like, we all know radio waves travel at the speed of light. So if your probe is out past Mars, it might take 20 minutes for a command from Earth to reach it.
Right.
And then another 20 minutes for the confirmation to get back. So we just factor in that 40-minute delay.
Exactly. The latency model assumes that while the signal takes a long time to cross that huge physical distance, the probe's internal clock is still ticking at the exact same rate as the clock on the wall at mission control.
Right. It assumes a second on Earth is exactly a second on the spacecraft.
But Bonaldi points out that near massive gravitational fields or at extremely high velocities, we are no longer dealing with a simple communication delay. That assumption just falls apart.
Because it's not just a bad video call.
Right. Under relativistic conditions, the system experiences measurable time dilation. The rate of time itself physically diverges.
Due to the velocity or the gravity?
Yeah, the velocity of the spacecraft and the gravitational potential of whatever massive bodies it happens to be near.
I want to make sure the mechanics of this are super clear for everyone listening, because it is so easy to default back to thinking about, like, a delayed internet signal.
Oh, absolutely. It's our only frame of reference, usually.
Right. So let's imagine a record player. If Earth is playing a song at 33 revolutions per minute, every note hits exactly when we expect it to.
Okay, I like this analogy.
So the latency model just means we're listening to that exact same song from very far away. So the sound just takes longer to reach our ears.
But the song itself is playing at the right speed.
Exactly. But time dilation is completely different. It's like someone is physically putting their finger on the edge of the record on the spacecraft.
Right.
Slowing it down to, like, 30 revolutions per minute.
The pitch actually drops.
Yes. The space between the notes stretches out. The probe is physically experiencing a longer second than we are.
That's exactly it, because the fabric of space-time itself is curving. When a probe enters a deep gravity well, like the orbit of a supermassive star or a gas giant, the actual geometry of space-time stretches.
It's just wild to think
It
about.
is. And from the probe's perspective, its onboard atomic clock is ticking normally, 1 second per second. But relative to an observer on Earth, that probe's clock is running slow.
Okay, so this is where we transition from a really cool physics concept to a completely terrifying computer science problem.
Yes. Because computers operate fundamentally on clock cycles.
Right. Every processor uses an internal oscillator to keep time. It dictates everything. When to read a sensor, when to execute a line of code, when to open a valve.
Every single control loop, every navigation calculation, and every resource scheduling protocol is mathematically dependent on those precise timing intervals.
So if you program an autonomous system to, say, initiate a thruster burn for exactly 5 seconds to achieve a specific orbital trajectory, it relies entirely on its internal clock to measure those 5 seconds.
Right. But if the physical rate of time for that internal clock has diverged from the mission time back on Earth, well, the probe's 5 seconds might actually equate to 7 Earth seconds.
Oh, wow. So the thruster just keeps firing.
Yes. It burns too long, the trajectory is completely ruined, and the spacecraft might just burn up in a planet's atmosphere.
And the most disturbing part of Benaldi's paper, to me at least, is how this failure actually manifests.
The silent failure.
Yeah. He outlines this scenario where a probe is orbiting a massive gravitational body. Its time is moving significantly slower than Earth's. But inside the probe's local bubble of reality, all its diagnostics say everything is fine.
Because within its local frame, the internal logic is totally sound.
It doesn't know it's failing.
No, not at all. The navigation systems are functioning nominally according to the parameters they were given. The onboard computer checks the thruster burn against its own clock, sees that it fired for 5 internal seconds, and just logs a successful maneuver.
It evaluates all its subsystems and basically reports back, status nominal, I did a great job. I'm really struggling with the self-monitoring aspect of this. Because if the probe's computer is executing its code perfectly according to its own processor, and its diagnostic sensors are reading that code perfectly, the machine has literally no way of knowing it's making a mistake.
None.
It is entirely blind to its own failure.
It's completely blind to it because the seconds it's using to measure its reality are now longer than the seconds used by the engineers who wrote its code on Earth.
Right.
So the fundamental timing assumptions embedded in its software are invalid. The sensor cycles just completely desynchronized from the mission parameters.
It makes me think of a musician playing in a symphony orchestra.
Okay.
Let's say one violinist has an earpiece with a metronome keeping them on beat. But due to some bizarre electronic glitch, their personal metronome starts ticking just a fraction of a millisecond slower with every beat.
Oh, this is a great way to picture it.
Right, so that violinist is playing their sheet music flawlessly. They're hitting every note in perfect time with the beat they hear in their ear. They absolutely believe they are performing perfectly.
To the conductor.
And to the rest of the orchestra playing on the standard time, this one musician is drifting further and further out of sync until they eventually become completely dissonant.
The tragedy of that violinist is the exact phenomenon Benaldi is warning us about in space. And he uses this very specific, almost haunting phrase to describe this state.
What's the phrase?
He says the autonomous system is not malfunctioning, rather it is correct within the wrong temporal context.
Wow. Correct within the wrong temporal context. That concept completely upends how we traditionally think about software engineering.
It really does, because we are so used to a binary world in software.
Yeah, exactly. The code compiles where it throws an error. The hardware is intact where it's broken.
We don't usually have to account for the environment itself altering the fundamental constants of the math.
Right. Benaldi formalizes this new class of error as frame relative validity collapse.
Which is quite a mouthful.
It is, but it's so accurate. The AI is making mathematically pristine decisions. The logic circuits are operating exactly as designed.
But because the temporal framework has shifted, those pristine decisions are entirely meaningless.
And potentially destructive.
Very destructive relative to the mission's origin point on Earth. He argues that our current self-awareness architectures in robotics completely ignore this. They basically just assume the metronome never changes speed, regardless of where the robot goes in the universe.
Okay, so if the system structurally cannot detect its own failure because its logic is internally consistent, we have to rethink the architecture from the ground up.
Yes. We basically have to figure out how to give a machine the ability to step outside its own perception of reality.
Which sounds impossible, but that leads directly to the core of Benaldi's proposal, right? The temporal coherence layer.
Exactly. He advocates for a completely new architectural requirement for deep space AI. It's a conceptual software layer that sits between the machine's raw sensor data and its decision-making engine.
It forces the system to constantly evaluate its own relationship with time before it executes any command.
And Benaldi breaks this layer down into three specific requirements, starting with what he calls temporal frame awareness.
So the system needs to actively realize that its internal clock might be lying to it.
Right. It has to detect and model its divergence from Earth's time.
But wait, if its own clock is the thing being warped by gravity, it obviously can't use its own clock to check its own clock.
No, it can't. That would be circular logic.
It needs an external anchor.
Exactly. The machine must look outside of its local reference frame. And Benaldi suggests several candidate signals for this.
Like what?
Well, the system could measure the desynchronization from Earth-based time signals, assuming it can still receive them clearly. Or it could calculate its own atomic clock drift based on its known velocity and gravitational environment.
Okay, but those have limits, right?
They do. Which is why the most robust and honestly fascinating method he proposes involves pulsar timing discrepancies.
Okay, using pulsars as cosmic clocks.
Yeah.
Let's unpack the mechanics of that because it sounds like something straight out of a sci-fi novel. Like, what even is a pulsar in this context?
So pulsars are rapidly rotating neutron stars. They are the incredibly dense remnants of collapsed stars, and they emit these intense beams of electromagnetic radiation from their magnetic poles.
Okay.
And as they spin, those beams sweep across the cosmos. If Earth happens to be in the path of that beam, we detect it as a regular repeating pulse of radiation.
Almost like a lighthouse.
Exactly like a lighthouse.
Yeah.
Because these objects are so massive and compact, their angular momentum is incredibly stable. They spin with a regularity that actually rivals and sometimes exceeds our best atomic clocks on Earth.
They are literally the universe's natural lighthouses.
Yes. So the spacecraft is equipped with sensors to detect these specific pulses, and it knows, based on its programming, exactly when the next pulse from a specific pulsar should arrive.
Okay, I see where this is going. So it compares the expected arrival time of that pulse with the time measured by its own internal clock.
Right. And if the pulses start arriving closer together or further apart than the internal math predicts, the AI doesn't assume the spinning neutron star has suddenly changed its rotation.
Right, because that's impossible.
Exactly. It assumes its own experience of time has warped. By observing multiple pulsars, what we call a pulsar timing array, the temporal coherence layer can triangulate not just its physical position in space, but its temporal position relative to the rest of the universe.
That is unbelievable.
It calculates its exact rate of time dilation.
It's literally teaching a computer to look at the stars, to figure out how fast its own brain is operating.
That's a great way to put it.
Okay, so once the system achieves that awareness, once it calculates that, say, its seconds are currently 10% longer than Earth's seconds, it has to do something with that information.
Which brings us to Benaldi's second requirement, parameter validity assessment.
Right, because knowing you're out of sync isn't enough. You have to adjust.
Exactly. This is where the AI takes active measures to prevent that frame relative validity collapse we discussed earlier. The system contains a parameter validation engine.
And what does that actually do?
Its whole job is to evaluate the continued validity of its mission instructions as a function of its accumulated temporal divergence.
This means the AI is no longer just a blind follower of Earth's commands. It's actually forced to critically evaluate its own instructions.
Yes.
So, if Earth sent a command to deploy a delicate solar array for exactly 30 seconds during a specific orbital maneuver, the probe has to pause. It has to realize that an Earth command relies on Earth time.
The temporal coherence layer intercepts that command. It applies what Benaldi calls temporal coherence thresholds.
So it does the math on the fly.
Right. The system calculates, okay, if my seconds are 10% longer, deploying this array for 30 of my internal seconds will expose the hinges to orbital drag for way too long.
It realizes it'll rip the solar array off.
Exactly. It assigns a confidence weighting to the instruction based on the current temporal shift. Rather than blindly executing the maneuver and destroying itself, the system determines the parameters are no longer valid within its current temporal frame.
And it modifies or aborts the action.
Correct. The machine essentially translates the intent of the engineers into its new reality.
And that translation process is absolutely crucial for the third requirement,
Right?
which Benaldi calls divergence communication.
Yes. Because when the probe finally transmits its telemetry and operational status back to mission control, it cannot just send raw data anymore.
Because if it simply transmits, hey, I executed a 5-second thruster burn, mission control will just assume it was 5 Earth seconds.
And that would lead to a catastrophic misunderstanding of the spacecraft's actual trajectory.
Right. The system must include its temporal context.
Benaldi refers to this as sending frame translation metadata through a frame translation interface.
It totally makes me think of dealing with currency exchange rates when you travel.
Oh, yeah. How so?
Well, if I log into my bank app while I'm in a different country, the number on the screen might say 100. But the actual purchasing power of that 100 units depends entirely on the exchange rate between my home currency and the local currency on that specific day.
That's a perfect analogy. The probe is essentially attaching an exchange rate to its telemetry.
Right.
It sends its data packets back to Earth, but the temporal coherence layer attaches this metadata that says, here is my current operational state, fuel reserves, and velocity. However, this data was generated in a temporal frame where 1 internal second is currently equal to 1.15 Earth seconds.
Basically saying, do not read my data without applying the exchange rate, or your mathematical models of my behavior will be completely wrong.
Exactly. The frame translation metadata ensures interpretability across entirely different experiences of reality.
It's just so brilliant.
When you step back and look at the aggregate effect of these three requirements, the awareness via pulsars, the parameter validation, and the divergence communication, it represents a profound shift in the philosophy of computer science.
We're moving beyond systems that simply execute logic loops in a vacuum.
Exactly. We are designing architectures that mandate a form of artificial self-awareness regarding the machine's context within the physical universe.
The system has to constantly interrogate its own reality. Are the parameters I was given still valid in the universe as I am currently experiencing it?
Right.
And while Benaldi's paper is heavily focused on deep space engineering, the core concept here feels deeply applicable to the decisions you make every day. Like frame relative validity collapse isn't just a risk for spacecraft.
Oh, absolutely not. The underlying principle is that logic is entirely dependent on its context. You can build the most rigorous, mathematically flawless, logically sound decision-making model possible.
But if the fundamental context, the environmental framework in which that model operates, shifts without the system realizing it,
Those perfectly logical decisions will become disastrously wrong.
it's such a powerful reminder that we have to constantly check our own temporal coherence, so to speak. We have to ask if the assumptions we based our plans on are still valid in our current reality.
And the paper actually leaves us with a rather profound philosophical puzzle to consider in that regard.
Yeah, the conclusion of this paper is wild.
Benaldi notes that under extreme temporal frame divergence, the defining question for mission control is no longer whether the autonomous system is functioning correctly.
Right.
The question becomes whether the system is functioning correctly relative to the frame in which its mission still has meaning.
That phrasing, in which its mission still has meaning, it implies that the purpose of the machine is totally subjective.
Yes.
If we send an AI so far out into the cosmos or so deep into a gravity well that its time frame diverges radically from ours, I mean, if decades are passing on Earth while only days pass for the probe.
The original engineers who wrote its code will be long gone.
Exactly. The society that launched it might have completely changed.
The instructions we gave it may no longer mathematically apply to its physical reality. And the data it sends back may arrive in an era where we no longer have the context to understand it.
It raises this massive question for you to mull over. At what point of divergence does that spacecraft effectively become an independent entity?
Right.
If Earth's time, and by extension Earth's history and future, no longer has any practical meaning to the mathematical reality of the machine, does Earth's mission still matter to it?
The temporal coherence layer might eventually calculate that the origin frame is too distant, both physically and temporally, to remain the primary anchor for its parameter validation.
Just cuts the cord.
It ceases to be an extension of human will and simply becomes an autonomous inhabitant of its own temporal universe.
Wow. So the next time you picture yourself as that director in mission control, looking up at those giant screens and tracking the telemetry of your billion-dollar spacecraft,
Yeah.
remember that the data you're looking at is just a ghost of Earth's time. Out there in the dark, your machine isn't just traveling through space. It is living by the ticking of a very different clock.